Hello, everyone. Welcome back. We are now looking at Chapter 3. This video is going to overview sections 3.1 and 3.2. Section 3.3 has its own set of videos, okay, a little bit of a different topic. And there's also going to be some supplement videos for the empirical rule. So this video will end with the empirical rule, but it generally can be a tough topic for students. That has been what history has told us. So there are some supplemental videos with some additional worked examples on the empirical rule that you're welcome to take a look at. So what we're going to be covering here is section 3.1 on the measure of center, and then section 3.2 on the measure of dispersion. So it continues our conversation about descriptive statistics. So chapter 2 was all about graphs. So we get the data, we represent it with a picture, and now what we do is we do some math, right? We try to describe our data numerically. And so in this section, we're looking at computing the mean, median, and mode. Should be very familiar to most of you. And of course, determining what the most appropriate measure of center will be given certain facets of our data. So let's get started. So the mean, sometimes called the arithmetic or arithmetic mean of a given set of data, is given by this formula. X bar is equal to x1 plus x2 all the way up to xn, and you divide by n, or more precisely, more succinctly, sigma of xi divided by n. So first of all, what is all this saying? Well, hi guys, how do you find an average? You add up all the data values you have and you divide by however many there are. That's what this is saying, okay? N is however many data values we have. Big sigma, that capital Greek symbol, Greek letter sigma, means add. Add the xi's up. What it's telling you and I is add up all the data values and divide by however many you are, okay? So x bar represents the sample mean. This Greek letter here with a U with a little tail on the front of it, this is known as mu. This is the population mean, okay? The population mean. So because it's a population mean, mu would be considered the parameter because it describes the population. X bar would be considered the sample mean, the statistic. Hopefully you remember that vocabulary from a couple of weeks ago in chapter 1, okay? All right, our job here is to compute the mean. Okay, there's our simple formula for X bar. We add up all of these data values. We divide by however many there are, which are 7. And this comes out to roughly 6.9. So again, I hope that is familiar for everybody, how to compute an average. Okay, we have an application. Safa has downloaded 5 new songs from the internet, and this should say she knows that on average the songs cost $1.23. So if 4 of the songs cost $1.29, what was the price on the 5th song she downloaded? Okay, so let X be the price of the 5th song, since that is something that we don't know. Okay, that's the unknown here. That's the question that's guiding us. We know the average has to be $1.23. So we set that equal to $1.29 times 4, since there were 4 songs at that particular price, plus the 5th song's price divided by 5, because we know that there are 5 songs. So we solve this equation. We multiply by 5 on both sides, and that gives us $6.15, which is equal to $5.16. That is the price of the $1.29 times 4. And so X here should be 99 cents. So that 5th song should be 99 cents. Okay, so this is an application to using averages. So sometimes we may not know all of the data values we're looking for, but if we know the average, I can figure this information out. Another application we have to the average is known as a weighted mean. Okay, now what is a weighted mean? This is the average of a data set in which each data value in the set does not hold the same relative importance. Now, a moment ago, I had us compute the average for a random set of data. You all just simply added up the numbers and divided by however many there were. The previous slide, you noted that we had a couple of different prices, but we still added them up and divided by however many there are. With a weighted mean, we kind of say which data value is a bit more important by using a weight. And the best example of this is your grade. Okay, your overall grade in the class is computed using a weighted percentage system. And so many classes use this. So what this means is if you look at the syllabus, you'll see that the final exam has a certain percentage, homework has a certain percentage, attendance has a certain percentage, quizzes, exams, worksheets, etc. That's what we mean by a weighted percentage, weighted mean, weighted average. So each one of them has a certain percentage. So Walter has a US history class, and we have a breakdown that tests are 40%, homework is 20%, etc. We want to know what his final grade is, if these were the final scores that he obtained at the end of the semester. So in order to figure this out, what we have to do is take each of his scores, 83, 98, 90, and 87, and we need to multiply them by the respective weights, 40%, 20%, etc. And then we need to divide that by the sum of the weights. So let's have a conversation about that. So his exams were 83, and as a percentage, the tests were worth 40%. So that was represented by 0.4. We do the same thing with homework, 98 times 20% or 0.2, quizzes, and the final. And you'll notice in the denominator, we sum the weight, 40%, 20%, 10%, 30%. And if you're paying attention, that should actually be 1. The sum of those percents are 1. The numerator simplifies to 87.9. So Walter's final grade would be an 87.9 in his history class, which, depending on the grading scale, more than likely will be a B+. So Walter, not bad. I think he would need to do better on his tests. Yeah. Now we have another example. We have Heather, who knows all of her grades in the sculpting class except the final. Okay, the points and grade that she earned is given below. So her tests are 35% of the grade. She got a 78. Class assignments are 20% of the grade, a 92. Semester project is listed there. And the final exam is 10%, but she has no idea what the score is going to be. So what Heather wants to know is, what does she need to do on the final to get a score of a 90% in the class? So Heather's trying to get an A. Okay, so it looks like 90% according to this grading scale. On mine, it'd be an A-, but anyway, who's counting? Okay. All right, so this is a typical question that students will ask. What do I need to do on the final in order to get this particular percentage? Okay, so we need to still use the weighted percentage formula that we have, okay? And you notice I listed all the information in the bottom right corner that we had, and I'm calling the final exam score X. Now, we take 78, which is her exam score, and we multiply that by the weight of 0.35. We do the same thing with the class assignments and the semester project, okay? Now, you'll notice that the last term in the numerator, X times 0.1, that X is the score she needs on the final exam. We multiply that by the 10%. You'll notice in the denominator, we are adding up all of the weight, 35%, 20%, 35%, and 10%. That's going to end up being 1. Now, this whole thing is equal to 90. Why is it equal to 90? Because that's the grade she wants. If she had said she wants an 85, we would change 90 to 85. Okay, so this is the grade that she wants. So we need to simplify this. So again, the denominator is 1. The numerator simplifies to 78.5 plus 0.1x. Okay, so getting rid of the 1 in the denominator, subtract over the 78.25, and we have 11.75 equals to 0.1x. So now the moment of truth, divide by 0.1. Ends up with a 117.5. Now, a moment ago, we had a note on the problem that said that the exam was out of 100 points. So I do not think that it is possible to get 17.5 points on the exam to get the score over 100. So unfortunately for Heather, this is not possible. She cannot get a 90 in the class. She needs to reevaluate a more realistic grade for herself. So now you all know how to compute your grade for various things. So now you don't need to ask me. But anyway. All right, the next measure of center that we look at is known as the median. Okay, the median is literally the middle number. All right, There's a bunch of wordy steps here that I'm actually going to explain on the next slide. So if you want, or through an example, so if you want to pause the video and read these, you're welcome to, but we're going to demonstrate how all of this works here in a moment. So we have two different types of data set, and we've been asked to find the median. The median is the middle number. So the first thing we need to do is put the data in order. Okay, so part A, I have arranged the data in order from least to greatest. Now you'll notice that there are 7 values here. So because there are an odd number of data values in the set, the middle guy is the median. So you notice it's with 6 circled, you have 3 data values on the left and 3 data values on the right. So 6 would be the median for the data set in part A. Part B, we repeat the process, put the data in order from least to greatest, but now you have an even number of data values, right? There are 8. So the middle one is actually going to be 7 and 8. There are 2. So when this happens, we actually need to take the mean. We need to add the 2 up and divide by 2, and the median we get is 7.5. Now, someone's going to say, well, wait a second, the median is not listed in the data set. My response, who cares? Okay, it doesn't matter. This is how it works when we have an even number of data values. No big deal. So odd number of data values, the median is literally the middle number. If we have an even number, you have to take the average of the middle two. So that is how we handle the median. The mode, this one is pretty simple. It's the most frequently occurring data value. Okay, if the data doesn't have a mode, we declare it to be no mode. If there's only one, we can say it's unimodal, 2 modes, it's bimodal, and anything more than that is multimodal. Okay, so frequently occurring data value. So if we look carefully at this data set, sometimes people put the data in order. It's up to you. Sometimes we can just see them right out. I see that there are 3 7s, okay, and that's certainly more than any of the other data values. I think 6 is listed twice, not good enough. So the mode here would be 7, and we would declare this to be unimodal. Now, I do want to make sure we're clear. The answer, when somebody asks you what is the mode, you don't respond unimodal. That's describing the mode. What I want to know is what is the mode? What is the mode? It's 7, and that makes this unimodal. Okay, if there was another mode, let's say 6 was repeated again 3 times, then we would say 6 and 7 are the mode, and this would be bimodal. Okay, bimodal. And there'll be some examples we'll work in class as well. Now, one of the important things that you're going to have to be able to do is to determine which of the measures of center is most appropriate. Now, let's talk about what we mean by a measure of center. So we've worked through examples of the mean, weighted means, the median, and the mode. What exactly do we mean by a measure of center? So center means describe for us a typical data value. That's what this is really getting to. So what do we mean by a measure of center? Measure of center is a typical data value. Many people will hear, you'll hear this expression, what does the average teenager do? What does the average college student do? What does the average millennial do, right? What does the average driver do? We're talking about the most typical case, right? What's the average shopper looking for when they go into Meijer or Kroger? Okay, those sorts of things. So it's just the most typical sort of thing. What's the average individual doing? So in order to describe this average or typical individual or thing, we use either the mean, the median, or the mode. So there are some suggestions here. So for qualitative data, we use the mode, plain and simple. That should make sense because the mode is qualitative. It's labels. We don't do anything with arranging stuff in order, right, from least to greatest. That doesn't make sense for labels. We don't compute anything in terms of a mean. So for qualitative data, you only use the mode. For quantitative data, it depends. If your data has outliers, then you need to use the median. Okay, if the data does not have outliers, then you need to use the mean. Okay, so it's going to depend on the data. So if the data has outliers, the median is the best case. Why is the median better if there are outliers? Because it's only based on position. It's only based on position. So you're going to have to pay careful attention to the data. So one of the exercises that you'll be asked to do on the homework exam and final is to determine the best measure of center. So part A says the t-shirt sizes, and they have them listed as small, medium, large, extra large of American women. T-shirt sizes as they're listed here, okay, in terms of small, medium, etc. This is labels. These are labels, qualitative data. So we'd have to use the mode. Okay, it has to be the mode. Part B says salaries for professional team of baseball players. So salary is definitely a measurement, so it's quantitative data. Now the question is, do we have outliers? Okay, if we think about a team, and even if you don't have any knowledge on baseball, are the salaries going to be relatively all the same on the baseball team, or are you going to have some really, really high-paid players? Well, I think it's going to be the latter case. You may have most everyone typically around the same sort of salary, and then the really good people you're going to have some crazy salaries. So for part B, we would need to use the median. Okay, part B is the median. Part C says prices of homes in a subdivision of similar homes. Okay, so if the homes are all similar, we should not expect to see any outliers. So I think for part C, the mean would be the best measure here. Okay, price, of course, is a measure, quantitative data. Part D, professor rankings from student evaluations on a scale of best, average, and worst. So because these are labeled as best, average, and worst, that's qualitative data, labels, categories, and so we have to use the mode. Now, we have some further application. If I give you some graphs, you're going to have to be able to tell me where the mean, the median, and the mode live. Okay, so the mode is pretty easy to spot. This is where the data and the distribution has its highest peak. Okay, the median is going to be the number that divides the area directly in half, and the mean is going to be pulled toward any outliers. Okay, so this is an important slide. All right. So first of all, and again, this would make for an excellent exam question, excellent homework final exam question. All right. We have a graph, and this was a histogram. And what we did is we removed the bars and we drew the curve over it. If you're wondering where in the earth is this coming from, this was a histogram. We took the bars away, left the curve. So first of all, this is what kind of graph? What is the shape? This would be an excellent first question. So the shape here, let's see, the tail's on the right side. So that is right-tailed or right-skewed graph. Okay, so what I need to look for then is, what is A? Is A the mean, median, or the mode? What is B? What is C? Are any of these repeated? Okay, let's see if we can make some sense of this. So A happens to be at the peak. Do you all see that? I hope you do. So because A is at the peak, that has to be the mode. That's the easiest one to spot, quite frankly, okay? Now, because this graph has a tail, we remember that the mean is impacted by outliers, so it gets pulled into the tail. So C has to be the mean. It's getting pulled away from where most of that data is. So B, it's going to take a little bit of imagination, but if you can picture it, if B would be the point that splits the area, that yellow, in half, so 50% on the left side, 50% on the right side. So you might have to use a little bit of your imagination to see if that works, okay? But these would be the three values, mean, median, and mode, for this sort of right-skewed graph. And if we flipped it to a left-skewed graph, then the picture would look a bit different. And we'll do a couple of these in class as well. If you have questions, let me know. But this, again, would make for an excellent, excellent question for an exam, homework, or the final. Just to give you a breakdown here of the mean, median, and mode, just so we have a sort of a nice summary here. So a good place if you want to pause the video and just give this a read over so you've got it for your notes. But some important pieces of information here, sort of summarize what we've been talking about so far. All right, the next section we move into is section 3.2, which deals with measures of dispersion. So 3.1 dealt with the various measures of center. So in other words, what are the typical data values? What do they look like? This section says, okay, well, that's all well and good, but we also might want to know how spread out the data is. And that's the idea behind the measure of dispersion. How spread out is my data? Okay, so our job here is going to be to compute the range, the variance, and the standard deviation. These are the measures that we deal with for measures of dispersion. The easiest one is the range. This is where you take the maximum data value and you subtract from it the minimum data value. If you were paying attention in the chapter 2 lecture video when we were dealing with splitting up the axes, I was actually computing the range, right? When I said what's the maximum value, the lowest value, then what's that range? What's the spread? That's what I was referring to. Okay, so we have some data that's been collected on call lengths, and we wish to compute the range for each of the data sets. So what we need to do in letter A is look for the smallest value and the largest value, and the same thing in part B. So if we look carefully at letter A, I see 2 minutes as the smallest and 44 as the largest. And as a matter of fact, part B is the same way. Okay, so the range for each of these would be 42 minutes. Now, part C has an interesting question. It says, what could be misleading about using the range as a measurement? Okay, could the range tell these two data sets apart? I don't think so. If you notice in letter A, there's a lot more variation among the call lengths. If you look in part B, nearly all the call lengths were 2 minutes, except for one at 44. But the range, if we just said to you, part A has a range of 42 minutes and part B has a range of 42 minutes, it can't tell the two apart. So there's no way to distinguish that there was a lot of variation in part A and part B, there was just this massive outlier. So outliers can be sort of hidden in the data with the range, not very visible at all. So range has some limitations. Now, we also have another measure of dispersion that's known as the variance, and the variance is actually related to the standard deviation, which we'll get to in a moment. So the variance, we have the variable we represent it by is sigma squared. So that is lowercase sigma. You might recognize uppercase sigma in the formula below in blue. That remember means add. So lowercase sigma squared is the population variance. And if we talk about the sample variance, we use S squared. So remember, population variance is the parameter, sample variance is the statistic. One describes the population, the other the sample. Okay, so this is a strange looking formula. So what is it telling me to do? So sigma means to add. So it's telling me to add. What do I add? Xi minus X bar. So it says I need to take each data value, that's what Xi is, and I need to subtract its mean. Then I need to square those, and I need to add all them up and then divide by the n minus 1. Okay, so we'll see if we can make some sense of that in a formula. Now, what the standard deviation is really just one more step. It says you take the square root of the variance. Okay, so that's what the standard deviation is. We simply take the square root of the variance. Now, what does the standard deviation? This is an important definition. It's going to come back a little bit later in section 3.3. It's also going to come back a little bit later in chapter 6 when we talk about the normal distribution. So a standard deviation is a measure of how much we might expect a typical member of the data set to differ from the mean. And I will make this even more exact. It's an average distance that data values are from the mean. So this is definitely a spread. It's the average distance a data value is from the mean. Now we have two ways to describe it. One is with the population standard deviation. We just use sigma, that's the parameter. And if we're talking about the sample, we use S. So previously was S squared for the sample variance, sample standard deviation, we use S. We just simply take the square root. So in order to compute the standard deviation, we again do sigma of Xi minus X bar, that quantity squared, divide by n minus 1, and then we take the square root of that quantity. So we're going to work an example here so that you get an idea of how to do this. Okay, we have heights of dogs. We have 5 of them. Okay, so we have 600 millimeters all the way down to 300 millimeters and 170 and a whole bunch more in between. So there are all of the dogs. Okay, so we need to compute then the standard deviation for all of these. So the first thing we do is compute the mean. Okay, so that should be 394. Add up all the heights, divide by 5. So hopefully that is fresh in our minds. Okay, now the reason we needed the mean is because the formula relies on the mean in the computation. So what I've done is I've put together a chart. Okay, and it says we can find the standard deviation using a table. So what I have done is I've listed all the measurements of the dogs, 600, 470, 170, etc. You'll notice in the formula, we have xi minus x bar. So that middle column is xi minus, and I don't know why the x bar is so small, but that should be an extended bar. The computer's having an issue with itself, but anyway. So what we need to do is we need to take 600 and we need to subtract 394. There it is. And so what we end up getting is 206. Okay. And then what we do is we square that. And so squaring that gives us 42.436. Now, some people wonder, why do you have to square the values? Well, sometimes you end up getting that difference being negative. Do you notice how you get negative 224 and negative 94? Okay. We don't want negative values when we take a square root, so we square them. That makes them positive. Okay. Now, because we are squaring things, it obviously made the numbers very, very large. In the formula, you'll notice that we take the square root. That's to undo the squaring. Okay, so that's sort of the derivation of the formula. So what I'm trying to figure out here is, again, how far are these data values from the mean? So 600 minus 394, we get 206. What that says is that we are 206 millimeters above the mean. 300 minus 394 is negative 94. That means that we are negative 94 millimeters below the mean. We are 94 millimeters below the mean, that particular measurement. That's what that is saying. So that is a distance, okay? So what we're trying to do then is average the distance. That's why we're dividing by this n minus 1. Now, if you did this right, the total in the middle column should be 0. Okay, that's not a coincidence. The grand total we have is 108,520. That, guys, is your numerator. That's what we have just figured out here. Okay, so that 108,520 is our numerator. Sample size was 5. 5 minus 1 is 4. So the variance comes out to 27,130. And what we need to do is take the square root of that to get the standard deviation. Okay. So the standard deviation for the heights of these 5 dogs is 164.71. Now the question is that good or bad? Okay. Well, let's go back for just a second. I want to look at the XI column. Do you see how the heights here ranged from 170 to 600? That is quite a range for the heights. There's a lot of variation. I know it's only a sample size of 5. So the fact that our standard deviation is 164.71, that's actually a lot. That is quite a spread. So the larger the standard deviation, the more spread out the data is. The smaller the standard deviation, the less spread out the data values are. And the question is that good or bad? That depends on the context, okay? It depends on the context. So that's what we have to sort of understand. Is that a good thing? Is it a bad thing? If I'm looking at it from the perspective of a teacher, and somebody told me that my standard deviation was, I don't know, 20 points, I'd be a little concerned because that means my scores are very much so all over the place, right? 20-point spread is quite a lot versus 5-point spread, right? Somebody says your standard deviation is only 5 points. That means that the students have performed at least either consistently well or consistently bad. But either way, there's a consistency that goes with that. Okay, some properties about the standard deviation. Okay, actually some additional information. Some of you may be wondering, why are we dividing by n minus 1 here? And this is to it says when given a choice, it is usual to average the square distances by dividing their total by n minus 1 rather than by n. This is because we need to draw some kind of distinction between the sample and the parameter. That really that's one popular opinion that is offered. Okay, so we use n minus 1 when we compute the sample standard deviation versus n with the population. S measures the spread about the mean, and we do use it to describe the spread of the distribution only when you use the mean to describe the center. And that will make some sense more so in chapter 6 when we deal with the normal distribution and as well as in section 3.3. But what this is saying to us, that first bullet point, is you can't use it with outliers. I mean, you can. Since the mean is impacted by outliers, standard deviation is going to be impacted by outliers. And the reason is because we need the mean in order to compute the standard deviation. Remember, the formula has X bar in it. If we are told that S is equal to 0, then there is no spread. That only happens when all the observations are the same. Okay, so if we had a data set and the data set was, let's say, exam scores and every one of them was an 80, and somebody said, okay, what's the standard deviation? It'd be 0. That would imply that all the scores were the same. Okay, so there was no spread. So anyway, as S is greater than 0 most of the other time, not most of the time, but the other times, this means that the more spread out these values are, the higher that S is. Standard deviation cannot be negative. Okay, cannot be negative. Okay, we have a application question here. Mark's looking into investing some money, and we have two different companies and the standard deviation of stock prices. And the question that we're looking at here is, what do the standard deviations tell us about the stock prices of the companies? So we have Profacto, which is $1.02, and Yardsmith, Yardsmoth, which is $9.67. So looking at the two standard deviations, I clearly see one is much higher than the other. So Yardsmoth has a lot more variation in their prices. So those stocks are jumping and falling and jumping and falling like crazy. Profacto with $1.02 seems to be a more consistent sort of price, right? There's not lots of variation amongst that. So what does Mark want to do? Well, it's up to Mark. Mark, if he's looking to make fast money, doesn't want to stay with the company too long, just wants to make fast money and get out, I would encourage him to look at Yardsmith because there's lots of variation. If Mark's looking for more long-term investment, then Profacto would have to be the way to go because that, right, is a much lower standard deviation, is not as much risk. So this is application of standard deviation. Now, we have a distribution of individual incomes in the US that's strongly skewed to the right. In 2004, the mean and median incomes of the top 1% of Americans were as follows: $315,000 and about $1.2 million. Which of these numbers is the mean? What an excellent exam question this would be. So first of all, I think we need the picture. There it is, right skewed. Okay, so the tail on the right side. I hope you agree that 1.2 million is on the right side and 315,000 is somewhere on the left, just by simple inspection of a number line. Okay, well, I remember from a little while ago that the tail is where the mean gets pulled into for a right skewed graph. So the 1.2 million has to be the mean. Okay, it's getting pulled away into the tail. Okay, and 315,000 perhaps is the median, since that's the other value. Okay, what we move into now deals with what we call the normal distribution. So we're gonna get into what's called the empirical rule. So normal curves, these are symmetric, they're single peaked, and they're known as bell-shaped. And the tails sort of fall off very quickly, so there are not very many outliers, if any. Okay. Now, what this means is that since the distribution is bell-shaped and it's symmetric, you see in the diagram in the bottom where it says the mean, we actually need to write the mean is equal to the median is equal to the mode. All three values would be 100% the same, and it makes sense. The mode is where the peak is. The mean and the median would split the data in half, okay, 50% on each side, and since there are no outliers, the mean isn't going anywhere. It's going to stay right smack dab in the middle. Now, if we decide to change the mean of the normal distribution, maybe looking at different sets of data, it's not going to change its shape, only the location on the x-axis. So it's just simply going to sort of slide down depending on what the values are if we consider the x-axis a number line. So for example, if I said to you the mean on an exam is an 80 and the distribution of scores was normal, then it's going to look at like the picture you have on the screen, and where you have mean, it's going to say 80. And if I said the other class had mean 85, it's going to be the exact same picture, only in the middle is going to be 85. Okay, so the picture stays exactly the same. Changing the standard deviation also is going to change the shape of the graph. So the standard deviation you notice in the diagram there is showing where the curvature of the graph changes. So a little bit of calculus. That first standard deviation there is where the graph's concavity changes, concave down to concave up. If you have no idea what I'm talking about, a little bit of calculus there, okay? Not to scare people. Now, we have something called the empirical rule, or the 68, 95, 99.7 rule, depending on the book you're using, or you hear people talking about this. What we know is from actually some calculus, integral calculus specifically, that about 68% of the data lies within one standard deviation of the mean. Within 2 standard deviations is 95% of the data, and within 3 standard deviations is about 99.7% of the data. That means most of the curve is filled in. So this is what the picture would look like. So again, 99.7% of the data, most of that curve is filled in. Now you might say, well, what's the point of this sort of exercise, understanding area underneath this curve? Well, we use this to understand a little bit more about how the distribution works with various sets of data. So I can, for example, say what percentage of individuals got within a certain range of scores on a test, if I know certain pieces of information. So here's an example to illustrate this. So we have teachers who grade on a curve. Okay, we have a lot of people ask, are tests curved? Is this curved, etc.? Well, I don't know that you would want us to grade on a true curve. This will explain why. So one way of doing a curve is to give everybody a C to the scores that are within one standard deviation of the mean. The teacher would give a B to the scores who are that are between 1 and 2 standard deviations, and anybody who's above 2 standard deviations gets an A. Anybody who's between 1 and 2 standard deviations below the mean gets a D, and below 2 standard deviations gets an F, okay? So again, I don't know that anybody would want us to grade on a necessarily true curve, because 68% of you would be getting a C. Okay, that's what we mean by a true curve. So I think what most people want is, if folks do bad on the test, you just want us to add points to everybody's score. I think that's the idea. Anyway, the question that we're asked is, if we have 200 students taking the exam, we want to determine the following. How many students would receive a B? Okay, so here is the normal curve, and we have some lines on here, and this is going to distinguish the different standard deviations. Now, what we're told is that a B is given to somebody who is between 1 and 2 standard deviations. So let's talk about the standard deviations we've got on here. In the middle is 0. And that's because the question is, how far am I from the mean? If I am the mean, I am a distance of 0 away from myself. So that's why 0 is in the middle. You'll notice on the right side, you have 1 and 2 standard deviations, okay? If we have positive standard deviations like 1 and 2, what that means is we are on the right side of the mean. If the standard deviations are negative, -1, -2, this means we are below the mean, okay? So those standard deviations, again, is an average distance that a data value is from the mean, okay? And that's where we are in this case. Now, all we want to know is how many kids out of the 200 are getting a B based on this information. Now, I have shaded in red the area where we get the B, okay? So what can we do? Well, I know that between -1 and 1 standard deviations is 68%. And I also know that between -2 and 2 standard deviations, we have 95%. How do I know this? Well, that's what the rule says a few slides ago. So if I deduct 95 minus 68, that leaves me with 27, okay? So that 27 would be in the area that I've shaded in red, and in the area between -1 and -2 standard deviations. Now, someone's going to ask, well, why? Because of symmetry, okay? The problem is I only want the area that is in red. So I need to divide that 27 by 2. I need to take half. That gives me 13.5%. That is the percentage of people who would be getting a B on this exam. Now, the question says how many. So we need to take 13.5% as a decimal, 0.135, times the 200, and we get 27. Okay, so 27 students would be the number who would be getting a B out of 200. This, again, is on a true curve, okay? Again, not sure that you all would want that many people getting a B. Just for purposes of illustration, the A range is 2 standard deviations or more. Look how small that area is underneath the curve. Those of you getting the C's would be between -1 and 1 standard deviation. That's 68%. That's a huge area. So again, that's grading on a true curve. All right, part B says how many students would get an F. Okay, so F scores are given for 2 standard deviations below the mean. So the area that is located here. Okay, fine. Well, the entire curve I know is 100%. So if I remove 95%, 95 is the area between -2 and 2, I hope we agree that we would have only 5% left. Now that 5% would be in the area to the left of -2 and in the area to the right of 2, okay? But the problem is I only want one of those. So what we need to do is divide that by 2. So take half. That gives us 2.5%. As a decimal, 0.025 times my, well, let's just say 200, not 2005. 200 students is equal to 5 students. So 0.025 times 200, make that correction, please, is equal to 5. So we should have only 5 students receiving an F. By symmetry, that means that only 5 students should be getting an A as well. I hope you all understand that. So anyway, that's grading on a curve, grading on a curve. Okay, one more example with empirical rule. And again, this is generally a tough topic for students, so there are some additional videos that cover this, so please watch those. We have larger animals tending to carry their young much longer before birth. So we have some information here about the lengths of horse pregnancies are roughly normally distributed, and there's a mean of 336 days, standard deviation of 3. And so we have some questions that go with this. So we'll repeat these questions here. Now, this problem differs from the last one in that we are actually told what the mean and standard deviation are, okay? So I'm going to return to my normal curve, and you'll notice that I put the standard deviations on here. Now, the language that I'm going to talk about in chapter 6, with the phrase that I'm going to use a lot, is that the normal curve only understands standard deviations. It doesn't understand other measurements like days, minutes, exam scores, etc. So if I go to the normal curve and I say 336 days, it does not understand what I'm talking about. Okay, so what I have to do is interpret it in terms of what the standard deviation is. Now, 0 as a standard deviation, remember what I said, in the middle always lives the mean. So in the middle here is going to be 336 days. There it is, okay, because that is the mean. Now, how do I get the first standard deviation value, number of days, on the right side of 336? And the answer to that is you add 3. Why 3? Because that's what the standard deviation is. So the value that's at the first standard deviation should be 339 days. The second would be, we add 3, 342, and then add another 3, 345. To get the negative standard deviations, we have to subtract 3. So 336 minus 3 again, minus 3 again. So I hope that makes sense. Happy to clarify again in class. Okay. So what this means now is if I go to this normal curve and I say to it 342 days, then I see, oh, 2 standard deviations. Now the normal curve understands me. Okay. So 345, that is 3 standard deviations. Now the normal curve understands. Now we're talking its language. Now part A wants to know what is the middle range of 68% of horse pregnancies? Well, I remember that 68% is, oh, I'm sorry, I labeled these. There we go. Standard deviations, number of days. Forgot about my special effects. 68% is between the middle -1 and 1 standard deviation. So that should be the range then of 333 days to 339 days. 68% is plus or minus 1 standard deviation on either side. So the answer here, 333 days to 339 days. Part B wants to know what percentage of horses are pregnant between 339 days and 345. Okay, so that looks like between 1 and 3 standard deviations only. So that is the area that I am looking at. Okay, well, by symmetry, we also have the area in green. There are 2 of them. Now, what you should notice is that there's an area that is not shaded. That's that middle area. So what I'm going to do is I'm going to take the entire curve, which is 100%, and I'm going to remove 68. Okay, and that leaves me with 32%. We are going to take that 32 and divide it by 2. That only gives me 16%. Okay, 16%. Actually, you know what? No, there was a mistake here. It says what percentage of horses are pregnant between 339 and 345? Okay, we had to have a correction here. Give me a moment. It's not going to be 100%. Here's why. We're only locked between 1 and 3 standard deviations only. You all see that? It's only between 1 and 3 only. So that shading should not extend beyond 3 and -3. So this subtraction should be 99.7 minus 68. That gives us 31.7. So make sure you make this correction, 31.7. So 99.7, that's 3 standard deviations away, minus 68, 31.7 divided by 2 should be 15.85%. 15.85%. So rounded up is about 16. So I guess I'm saved myself a little bit there, but technical answer should be 15.85%. Sorry about that oversight. So 339 days and 345. So it technically stops at 3 standard deviations. So once again, the steps should be 99.7 minus 68. That's 31.7. 31.7 divided by 2, 15.85. And somebody might say, well, you round up at 16. Well, technically 15.85. And the last one here, we've got how long must a horse be pregnant to be considered in the top 2.5%? Look at the wording here, how long. So how long means how many days. Now, top 2.5%, I hope you all understand, is somewhere on the right side. Okay, just by simple inspection, top 2.5%, somewhere on the right side. Okay, now if there is a top 2.5%, there also has to be a bottom 2.5% by symmetry. If we total those, it would be 5%. Okay, now if we take 100 minus 5, that gives us 95%. That implies 2 standard deviations above or below. So this means the value for the top 2.5% would have to be at 342 days. So the area to the right of 342 days, that has to be 2.5%. And that concludes this portion of the Chapter 3 video. So again, there is video on section 3.3, so do take care of that. That is on the measures of relative standing, dealing with ranking. And we also have supplemental videos on empirical rule.